the lessons leading up to now have all been kind of background skills that are necessary for even talking about physics. It's like you have to learn a language before you can actually communicate about things in that language, and so that's what we've been doing so far. This is kind of the first lesson that's really talking about kinematics, the study of motion, distance and displacement. So we're going to talk about distance and displacement, speed and velocity, and acceleration. It's all talking about motion and how motion changes. So kinematics is the study of motion, but it's independent of the forces that are causing that motion. So in order for something to start moving, there needs to be some sort of force that's starting it moving. But we're going to ignore the force part for now, and we're just talking about the relationships between the aspects of motion. And so the first one we're talking about is distance and displacement. So first of all, kinematics deals with describing motion. In a way that doesn't consider the forces involved. Let's just put that in there, so in case you hate blank blanks, now you've got it. So distance is a measure of how far something travels. You already know that. Or the number of meters between two objects, or between two cities, or something like that. And it doesn't really take into account the direction between two things. So when I'm running 100 meters, I don't need to tell you that I'm running 100 meters north. The north part doesn't really have anything to do with the distance I've traveled. It's only the 100 meters part that matters. Displacement, however, describes change in position. So although when I run 100 meters, I've changed position by 100 meters, probably, displacement is a bit more specific about it. We have to take into account the direction that change in position happened, and the path might make a difference as well. Not to displacement, but to the difference between distance and displacement. So let's take a look a bit more closely at that. It describes the change in position of an object during some sort of time interval. It needs to be described by magnitude, that's size, how much change was there, and the direction of the change. Okay, so I ran 100 meters north, ran 8 meters west. You know, it is a vector. A vector requires both size and direction. And usually we represent vectors using arrows because that's the easiest way to show direction. And that's what we've been studying in the previous couple lessons. So whenever you see this symbol right over here, that's the Greek symbol delta. And in physics, and probably in science, in every branch, it means change in something. So we have used change in D right here to describe or to denote displacement, change in position. You will see other ways of writing that down as well. You might see change in X, where X is position, and so this would be change in position. So you might see that. There are a couple other ones that I've seen as well, but usually those are the main two ones. In this course, we're going to use change in D, where D, with an arrow on top, is position, and change in D is displacement. So delta describes a change in something. In our case, change in position is what we're talking about. And so this formula right over here, this is the formula for calculating displacement. If you know the ending position and you know the starting position, then if you subtract them, that gives you the change between them. This formula is most relevant if you are, say, talking about coordinates on a Cartesian plane. Okay, so if you know the x and y coordinates of something at the beginning and the end of its motion, then if you subtract those two things, you get the change in position. Now, most often we're not going to need to use a formula for calculating displacement. You're going to be able to calculate it out just thinking it through. So, when we're working with vectors, directions are very important and they have to be considered. Vectors, by definition, have a size and direction to them. You can't forget the direction part or you've missed half of the problem. So different directions are often indicated by using positive and negative. We assign positive or negative to the directions. So we're using positive and negative. Okay, and so maybe in this question you are going to be talking about something that's dealing with west and east. And maybe you'll need to do some sort of calculation involving vectors, east and west vectors, and maybe you want to call east the positive vector and west the negative vector. Okay, they're opposites, and so going west is the same thing as going negative east. That's weird to think about maybe, but that's how it works. You also need to have a reference point in mind. So if you have traveled upward from underneath the water, your reference point might be the surface of the water. And so then you might have traveled positive 10 meters above the water, but maybe in total you've traveled 15 meters because you started 5 meters below the water. So you need to pick some sort of reference point. Often that will just be obvious, but sometimes that will need to be done. So you pick a fixed point, one that is not part of the motion, and all measurements are taken from that point. Let's do a couple examples. You are in Steinbach and decide to go for a drive one Saturday afternoon. You drive 8 kilometers south of Steinbach when you decide to turn around and drive 13 kilometers north. What is your distance and what is your displacement? Let's draw a little picture here. So here we have Steinbach. That's where you started. We're going to assume, for the sake of simplicity in this problem, that Steinbach has a size of 0. It's a point. Okay, that's just going to make this a little bit easier. So you drive 8 kilometers south of Steinbach. There's your 8 kilometers. When you decide to turn around and drive 13 kilometers north from there. So there's where you ended going south, and now you're going to go north from there by 13 kilometers. And this is where you end up now. So this is 13 kilometers. So, distance cares how far you traveled in total. So your distance is going to be 8 kilometers plus 13 kilometers. Doesn't matter what direction they were. You traveled 8 kilometers and then you traveled 13 kilometers. If you did that on your bike, you'd notice that you went 8 kilometers and then 13 kilometers, right? So this is D equals 8 plus 13. This is kilometers. And that equals 21 kilometers. That's it. You can do that. I'm sure you've done that a lot of times before. Displacement is going to just take into account your starting position and your ending position. So here's your starting position. Here's your ending position. And so from the start to the finish, you actually went this way in total. This is your displacement. And that's important. So you just take into account, where did I start and where did I end? The path you took to get there, that doesn't matter at all. That's distance's job. Displacement is just, where did I start, where did I end, and what's the difference? So the difference here, your displacement, is 13 north minus 8. right? So this takes into account that you went 8 kilometers south, and from there you went 13 kilometers north. So if we take 13 and subtract that 8, so if we take this 13 kilometers here and subtract this 8 kilometers from it, that will give us what the change was in total. And so 13 kilometers minus 8 kilometers gives me 5 kilometers. And my total change was to the north. So this is my final displacement, 5 kilometers to the north. You decide to walk to your friend's house. You walk 1.2 kilometers east and then 2.2 kilometers north. What is your distance? What is your displacement? So first of all, from your reference point, wherever that is, so let's say that's your house. So here's your house. You walk 1.2 kilometers east, and then you walk 2.2 kilometers north. Like that. What is your distance? What's your displacement? So this is 1.2 kilometers. This is 2.2 kilometers. So hopefully the distance part is pretty straightforward. Distance equals 1.2 kilometers plus 2.2 kilometers. It's all the distances that you traveled put together. And that gives you 3.4 kilometers. No direction, right? Distance doesn't care about direction. Displacement, though, does care about direction. So we're going to take our starting point right there and our ending point right there. We don't care about the path to get there. We're just going to go beginning to end. This is my displacement. So how would you figure that out? I think that you would remember if you went back to the components section, right? So this is figuring out the hypotenuse when you have the opposite and adjacent sides, or when you have the other two legs, and that would be using Pythagorean theorem. So the displacement if we're doing a squared plus b squared equals c squared, this would be c. This displacement here would be the c part. So c squared equals a squared plus b squared, but I'm just going to square root it right away. And so the displacement is 1.2 squared plus 2.2 squared. Now we need to remember that this is all kilometers. I just haven't written the kilometers in here just for the sake of space. But it's a good practice to throw in the units absolutely everywhere so that you don't forget them at the end. We need to remember that we're dealing with actual quantities of something. We're not just dealing with raw numbers. So displacement then is equal to 2.5 kilometers. But with all vectors, we need a direction on it. And so our direction is going to come from this angle here. We're always looking at what's the angle at the beginning. So this was our starting point right there, and so the angle that we need to use to determine the starting point is the one right here that uses that starting point as its vertex. And so we started measuring toward the east, and we rotated up toward the north to measure that angle, and so it's going to be east something degrees north. So I'm going to write down east and north here, and then I need to figure out what the angle is. And so we can use inverse tan. Again, now we have the hypotenuse as well, so we could use that, but it's better to use the unrounded numbers. Inverse tan of 2.2 over 1.2. Right, because if we're standing at this angle over here, then this is the opposite side, and this is the adjacent side. Opposite divided by adjacent is tangent, so if I do the inverse tan of 2.2 over 1.2, I get 61 degrees. And so 61 degrees is what goes in here, and my final displacement is 2.5 kilometers east, 61 degrees north.